Okay, I want to remind you, or maybe you didn't know, about the class videos. So if you go on Blackboard, over here to the left, and hit class videos, I have posted them on YouTube, which the video is everything you see on the screen. It's not a video of me, thankfully. And the audio is then what I'm saying. Okay? One thing I'm going to do is, for the Calc 1 course that I taught this morning, we did one day on linear function. And it is a great overview of Module 2. It would be a great video for you to watch. We delved into almost everything we talked about throughout Module 2 and built up to linear function. So I would highly recommend. I'm going to post that in this list along with our classes, that one class. So just look for that 270 class from the 14th. I'll post that today. That would be a great class for you to watch as well. Okay? So, and then I understand sometimes some people go here and they don't see anything. Okay, so it's just your browser. So I know Firefox works. There's some browser that just doesn't show, these videos don't show up. Okay, so I know Firefox works. And there's others too, okay? So you just got to figure out what browser you're going to use that's going to be able to find those. Any questions on the videos? Okay, we're talking about this box problem. So, standard sheet of paper, 8.5 by 11, right? What do we do first? We pick a size for squares to cut out of the corners. All those squares are going to be identical. Okay? The size of the square cut out, is that a changing quantity or a constant quantity?
The size of the cutout.
The size of the cutout. Constant or changing? If you did your homework, you know this is a varying quantity. We can choose a tiny little square to cut out. Well, first of all, we can choose a square of 0 size. Here it is. You get a flat piece of paper with no volume. Okay? Perfectly physically possible mathematical situation, so we want to include x equals 0 as a possibility. Is it okay? I know it's really uncomfortable for just talking to students in past semesters. But we want to just accept mathematically that it's a physically possible thing to do. We can cut out no squares, and we get a piece of paper with no volume. It's okay. What we cannot do is cut out like a negative square. So 0 is the smallest, but we can't cut out a negative square. We can cut out a very, very small square. And as soon as we actually cut out a square, we get some kind of volume. Small squares make low, flat boxes. Large squares make tall, skinny boxes, okay? With smaller area of their base. So that's the setup. So we were defining, last time, we know that what was the width of our original sheet of paper? 8.5 inches. And we wanted to use that 8.5, and then we called, since it's a variable for this side length of the cutout, x, we were coming up with, now given that size, that square can vary, and the width is originally 8.5, then what is the width of our box? That's going to be an expression in terms of x, because x can change. And what did we say it was?
8.5.
We start with the 8.5, and whatever x is, we're going to lose 2 of them. We're going to lose an x on this side, and we're going to lose an x on this side. So the resulting square is going to be the original 8.5 minus 2x. Similarly, the length, what's our starting length? 11. And then we're going to lose 2 this way, or so lose an x here, and lose an x there. So 11 minus 2x. And what's the height of the box in terms of x? When you fold up those flaps, the width of the flap is your square cutout, and that ends up being the height of the box. Okay, and then we talked about, so this length, or I think we talked about the width. So we said, what's the smallest value of x What's the smallest value of x that's physically possible? Okay? And what's the largest value of x that's physically possible? 8.5? Let's take a look. So what's going to limit how big we can cut that square? The width or the length? The width. And the square, the biggest square we could cut would be half of the width. You see it? The biggest square we could cut would be half of the width, so it would be 4.25. So then, as x varies from 0 to 4.25, what are our possible values of width, then, of the box? So what's the lowest width? So look, you're looking over here. Sorry. Whoa. Over here, this is the width, right? So what's the lowest possible width that we could get? And that corresponds to x as what? Which x value gives us the lowest width? Does x equals 0 give us the lowest width? Here's x equals 0. What's the width? The width is 8.5. What value of x gives us the lowest width? 4.25. It gives us a width of 0. I'm showing you the box that has a width of 0. It ends up being a flap of paper that you fold up like this. So you have no volume because you have no width. So the width can go from 0 to, what's the largest width we could have, physically possible? That corresponds to when x is, so when we don't cut out squares, that's the biggest width we can have, and that's our 8.5. Okay, I want to talk about this equation here.
So the corresponding length with that,
Yeah.
is that
Okay. What's the greatest length you could have?
the greatest length is 11.
11. Now,
Smallest
what's the
would then
smallest
be
length you can get?
8.5 minus 11, correct?
What do we think? What's the small? He wants 8.5 minus. So that's a negative number. So the smallest length that we can get,
11 minus 8.5.
11 minus 8.5 is what he says. The smallest length we can get is this dimension right here. What is it?
Okay.
It's 0? How would we get that smallest possible length?
From the red dot to the next blue line.
From here to here.
So it's
So what's this? We start with how far?
11.
11. And we're going to subtract.
8.5.
Yeah, you're right. Yeah, exactly. 4.25 on that square. 4.25 is minus 8.5. That's right. So that gives us a least width, or sorry, smallest length is 2.5. So the length varies from what to what? The length can vary from 2.5 to 11. 2.5 to 11. Does it make sense? Okay, I want to look at this width formula, and I want to ask a question. Is width proportional to square cutout length? Those are the two quantities we're working with together here. X and W. Are width and square cutout length proportional? So what was our formula again?
8.5 minus 2x.
8.5 minus 2x. Is width proportional to x, square cutout length? Yes or no?
Yes.
Yes, width is proportional to square cutout length. Agree with him?
Yeah.
Yes. People are nodding their heads. Let's try it. When x is 0, what is the width? when x is 1? What's the width? One more time, when x is 2, what's the width? Okay, how can we check to see if x is proportional to width? What would have to be true? Don't forget everything we learned. Common ratio, constant ratio. Constant multiple. Scaling factor. Take your pick. All you have to do is check one of them. What do you want to check? Scaling factor. Okay? What would I have to scale? Here I'm scaling from what? I'm doubling the square cutout length. Therefore, what would have to happen? Double the width. So that would have to be 13 point. It's not even going up, it's going down. Do you see? It's really bad. No way, Jose, not proportional. Don't forget what you learned.
Can you go over, just show there's proportional on the other two ways? Because I don't feel like I ever really got the
Okay, so videos. Yeah, we spent many classes on that. So go back to the videos or office hours. Yeah.
Okay.
Yeah. But so one way is saying if you double the first quantity, if they're proportional, you got to double the second, and that does not happen. This would need to be 13. Okay, so that was scaling factor. Okay, so not proportional. Does width vary at a constant rate with cutout length? Does it vary at a constant rate with cutout length? So this is the end of Module 2.
Yes.
And how would you know that? How do you check that mathematically? What does it mean for two quantities to vary at a constant rate? What's the key to that? The mathematics behind it.
For each point it is decreasing by 2 inches.
Okay, so in general, what does it mean for two quantities to vary at a constant rate? Yes, sir. What about it? He said change in y over change in x. What about it? Okay, change in y over change in x is constant. And what is another way to say that is what?
Average.
No, we're not talking about average here. We're not talking about average. Change in y over change in x. That's a ratio. The ratio is constant. So what are we talking about there? Proportionality of the changes in the quantities. Okay? So maybe it'll click, maybe we can retain it today, because we've done it many times. If the change in the quantities, the change in y, in this case the change in w to the change in x, if the changes are proportional, and one way to talk about the changes being proportional is they're in a constant ratio. The change in w to the change of x. If that's constant, then we have proportionality of the changes, and then we have the quantities x and w vary at a constant rate. Yes or no? So let's try it. Let's do some changes in x and changes in w. What if I change the x by 1? How much does w change?
-2.
How much does it change?
-2.
-2. How about if I change x by 2? How much does w change? -4. Okay, let's do one more. So let's make x equal to 4. If x equals 4, what's our width? 0.5, right? So now I want to change by 3. If I change the x value by 3, delta x is 3, how much does delta w go down? -6. Are the changes proportional? Yes. Okay. Try anything you want. Scaling factor. What is the common constant ratio? All right, so the constant multiplier. -2. All right, it's -2. And what did we say? What is that relative to the graph? That slope. Okay, and there it is, right here in the formula. We know that this is slope, and the slope is our constant multiplier that would give us the change in w given a change in x. So let's interpret it. The number -2. We interpreted it before. What does it mean? What does that number -2 mean? Talking about comparing the cutout length and the width. What does -2 mean? What's that? Okay, it's the rate of change. -2 is the rate of change, true. What is that? What does it mean?
For every decrease in w by 2, x is going to drop.
Do it the other way. Do the x first.
So every change in x, for every 1 change in x, 1 inch in x, then w is going to change by -2.
Okay, he said for every change of x, if we increase x by 1 inch, if we make the cutout 1 inch greater, what will happen to the width? It will decrease by 2 inches. For every 1 inch that we increase the cutout, we're going to decrease the width by 2 inches. It's relative size. Relative size. Whatever you increase the cutout length by, the width is going to decrease 2 times as much, or it'd be -2 times as much as what you increase the cutout length by. Okay? So there's the graph of it. This is width. So when x is 0, the width is 8.5. We talked about that. And when you go all the way to 4.25, the width is 0. And this is showing that no matter how you change x, so if I change x this much, how much will the width change? How much will the width change if I change x this much? It'll change by -2 delta x. And how about if I change the width this much, or the cutout length? How much will the width change? -2 times that. So we do have constant rate of change there. The constant is the relative size of changes of width to changes in cutout length is -2, meaning that picking any change in cutout length that we want, the corresponding change in width will be -2 times that. This is all reviewed. This is all reviewed. Does it ring a bell? Okay. So are x and w proportional? No. Are changes in x and w proportional? Constant rate of change, linear function. Right. Okay, let's look at the volume. How do we find the volume? So going back. So if we got our length is 11 minus 2x. Width is 8.5 minus 2x. Height is x. Volume of the box. What will the volume of the box on the right side of the screen be?
All of those multiplied
General formula for volume is?
length times height.
So it's going to be our length times width is volume proportional to cutout length? Is volume proportional to cutout length? Are changes in volume proportional to changes in cutout length? I'm letting you think about it. There's our formula. Are the changes proportional? No, he says. Here's our graph. Did you graph this on a calculator for your homework? Did you get this? You got something like this. Are changes proportional? Changes of x to changes in y, are they proportional? Let's take a look. So in number let's just do E. So indicate a change in the cutout length from 2 to 3. Indicate a change in this graph. How would I do that? How would I indicate a change of cutout length from 2 to 3? Can you imagine what I will draw on the graph to do that? Horizontal line, where? Starting when x is 2, so at that point right there. Over 2, I'm going to guess it's about, how did I do? About there? This is a delta x of 1, starting at when x is 2 and ending at when x is 3. So what is the corresponding delta y for that? That would be the change in volume. So to do that, I'm going to need to go down to the point where the length is 3. When I increase the cut length from 2 to 3, does the volume increase or decrease? Decreases. What about if I went from, there's another earlier problem that said from 0.5 to 0.75. Let's do that one. So here's, okay, so there's 0.5. I want to increase x from 0.5 to 0.75. Always do the x first. So you do x, and then you see what y does in response. Let's see how good my left hand is. When we start at a cutout length of 0.5 and increase the cutout length, what happens to the volume? Goes up. It's when I have a real shallow box and I increase that cutout length and make it taller and a little bit, then I get a larger volume. What happens if I start from a cutout length of 2 and increase the volume? It goes down. See? It goes down. So our change is proportional. No, I mean, yeah, so sometimes it goes up and sometimes it goes down. Can't possibly be proportional, right? And we also know that if the changes are proportional, what kind of graph do we get? Straight line. This is nothing like that, okay? So let's do this. You were asked to calculate the change in volume when x went from 0.5 to 0.75. So we've got the volume, the formula for volume is 11 minus 2x, 8.5 minus 2x times x. How am I going to find the change in volume associated with a change in cutout length of 0.5 to 0.75?
Plug in x root. That equation.
So here's what I want to do. Since x changed by 0.25, watch this. My change in x was 0.25. I'm going to take 0.25 and plug it into the volume equation, and it's going to give me the change in volume. Right?
No,
What do you mean no?
because then now you're just finding out the volume of.
If I plug 0.25 into the volume equation, so I'm going to represent that here. 11 minus 2 times 0.25. Haste makes waste. 11 minus 2 times 0.25 times 8.5 minus 2 times 0.25 times 0.25. What will that calculate? What will the output be? Think about what will it look like on the graph. So how could I represent this value of volume on the graph? What will it be? What's that? It'd be the y value for what? That's right. When my x is 0.25, which is right there. This over here, plugging in 0.25 into the volume, it gives me this volume 20, let's see, measurements. It gives me 21 cubic inches. Is that the change in volume? That's 21 cubic inches right there when x is 0.25. Is that the change in volume when x goes from 0.5 to 0.75? Do you see that's what the question is asking for is this. What we just found was plugging 0.25. This is I'm going over this because it's a really common mistake that students make. And you got to see that the change that comes from a change in x has to be the difference of the volumes. It's not, you don't take the difference of your change in x and find the volume for that, because that would give you this value down here. That's the 21. So rather, to find this change in volume, what would we need to do? Plug in 0.5 for x and get this one and this, okay? And then we'd also plug in 0.7 and get this one. Right there, that's your change in volume, and subtract. So we'll just do it real fast. So it's going to be different than 21, right? So let's go to 0.75 first. What's the volume? Shoot. 49.88. Okay, got it. Write it down. Minus, so that's this one up here, 49.88. Oh, I had it. It's very sensitive. That's not it. That's not it. Hold on. I'm trying. Sorry. Stop. Right there. What is it? 37.5. Take the difference of those two. What do you get? Nothing close to 21. Do you see? 12.3. 12.33? 12.38. 12.38 is the change in volume as the cutout length goes from 0.5 to 0.75 versus 21 if you were to plug 0.5. Represents something totally different. That represents the volume if the side length was a 1/4 inch. Okay, any questions? Any questions on, you did the module 1 worksheet, or module 3 worksheet 1. Any questions from other stuff in that worksheet that you wanted to talk about? So this thing about, when one thing changes, how does the other change? This is like key in calculus. That's why we're spending so much time on it. This whole idea of how quantities change together. So being able to calculate a change in volume given a change in x, really knowing that process is really important. And this is a common mistake. I tried to spell that out. So if you need a change in volume for a change in square cutout length, you need to get the volume at the one cutout length, the volume at the other, and then see how much they change. So that'd be difference, right? Subtraction. There were a couple questions here.
Can you go over Fri Sept?
Okay, so they're saying for what cutout lengths does the volume decrease? So what would it be?
0 to 1.585.
So from 0 to 1.85, is the volume increasing or decreasing as you increase cutout length? Increasing, right? So they asked about decreasing, is that right? So for what x values does the volume decrease?
1.585 to 4.
That's it, yeah. So when you're at 1.585 or greater, for those cutout lengths, your volume's going down as you increase the cutout length. And we saw that here in this example here. For a positive delta x, delta v is negative. Is there another question? Yeah.
How do you find when flat is up to be like the top most? Like, how do you figure out that's where it starts going down?
So on your calculator, there's a max button. You can just use the technology to do it for you. But that's actually, to do that mathematically is a calculus question. So we don't have the tools to do that yet. But you've got, your calculator has a max button on it, or you can trace and estimate. Yeah. Sure. Yeah, definitely.
Just start plugging in numbers.
We're just, right now we're just getting a feel for how two quantities change together. So we're asking all these questions about, if you increase x, how does v change? And we want to really get a good hold of that. So things like that, like what's the intercept, or what's the highest point, you can just use your calculator to get those answers. Okay. This. Okay, so I want to talk about this thing called a function. We had this formula. Let's write that formula again. V was length 11 minus 2x times 8.5 minus 2x times x. And the idea is we can pick any square cutout length, plug it into the formula, and it spits out what? The volume of that corresponding box after we fold up the sides. Okay? So it's the idea that we can choose lots of different cutout lengths. 1/2 inch, 3 inches, 4.5 inches. And for each one of those, it's giving us a different volume based on the situation. So this is the idea of function. Okay? A function describes how input values are mapped to output values so that each input value is mapped to exactly one output value. So what was our input in this equation? What's our input value? Cut out side length. And the output then? Volume. So if I decide on a cutout length, is there one particular volume associated with that? It's determined, right? It's determined. That's the idea of a function. Okay? So you can think of it as a machine. The length of the side of the cutout goes in this formula. This is how the machine works. It takes that number and it cranks on this formula and it spits out a volume. This is the idea of function. Really important idea. This is where we've been talking all about looking at visually how two quantities vary together. So now this is the symbolic side of it. We use functions to represent symbolically how two quantities vary together. Okay? Input, this is in general. Output, rule. Okay? So the input, the rule operates on the input and spits out the corresponding output. So this is a powerful idea. So this is where calculus lives. It lives in the land of functions. It lives in the land of two quantities changing together. Okay? So how do we do it? So this, we know our output is volume. This f is the name of the function. You can name it anything. You can name it g. You can name it h. You can name it b. Whatever you want. Okay? F is the most common. You've seen that a lot in your previous courses. F for function. But it's just the name of whatever function you're using. Okay? The input then is in the parentheses. This is not f times x. Do you see that? It's not f times x. F of x. This is the name, and whatever's in the parentheses is your input into the function. And the rule tells you what to do to the input. The rule tells you what to do to the input. So there's the rule. So I'm going to go back, do the whole thing again. So what I want you to do is, don't do any calculations. Just represent using this notation the volume when the cutout length is, what do you got in there? If you look on page 89, 1.5. Let's just do the first two. You don't have to do all four. 1.5 and 2.7. You're not doing any calculations. You're just using this notation to represent what the volume would be when the cutout length was 1.5, and then when the cutout length is 2.7. Just those two. You don't have to do all four. Two is enough. Page 89, number 1, A and B. Just represent. Just represent. For A, it's x is 1.5. For A, you're doing the cutout length of 1.5, and for B, you're doing the cutout length of 2.7. No calculating, you're just writing. You're just representing it. That's when x is 0.5 inches. This was what the volume would be, how it would be represented.
So is this 0.5 v of 0.5, or is this?
No, that's the x. That was the height. So yeah. So it's length times what times height. They just put height front. So how do we represent a volume when the cutout length is 2.5? We could write volume equals f of 2.5, and then we could put that into the rule, and it would be 8.5 minus 2 times 2.5 times 11 minus, the natives are getting restless. Times 2.5. I hope not.
Either way.
I wrote down 2.5. So what would it be if it were 1.5? I think you can do it, right? So here's the key. Whenever we want to represent the volume when the cutout length is 2.5, we don't want to write that whole thing out. We know how to get it using the rule. But we want to keep it simple. So what we want to write is this. This is a powerful tool, so we don't have to sit here and talk about, final values. We can just write that and put it in lights. Okay? This is all we need. Right there, if we know that the function f outputs volume for an input of cutout length, then this notation right here, f of 2.5, what does it mean? If you look at that, you know that that is the same as?
Everything we just put up.
Okay, so I heard the y, everything we just put up there in the answer, but no one said what it is. Say the whole phrase. It's like, what quantity is it? It's the volume of the box when? No, when the cutout length is 2.5. That thing is the volume. It seems easy, but then you start working with it, and my experience is students have a lot of trouble with this, so that's why we're going slow. That is a number, f of 2.5. It's the, what number is it? The volume of what? Of a box when cutout length is 2.5. Okay. So what I want you to do is turn to page 90. I want you to do 2a and b and 3a and b. There's no calculations in any of these questions. It's all writing out meanings. For B, let's just do 4.1. Just do it one time. Part B, don't do it 3 times. Just the one time with 4.1. Say it again. Yeah, what we just did, like there's the name and the rule and the input and the output. Yep. For part B, just do 4.1. If you want me to check what you got, I can check it or the person next to you can check it. You're saying that B is the input. They told you the name. B is not the input. I see a lot of you putting that B is the input. Did they tell you that B was the name of the function? Pretty sure they did, right? B is the name of the function. Saying that B is the input. The name of that. B of what? So you're going to show the function of the parentheses, showing what your input quantity is. You want to show the parentheses showing what your input quantity is. It's the square cutout line, right? See, you're saying B is the input. B is not the input. I see lots of F of B. It's not right. It's not right. They said B was the name. B was the name. What's the input? What symbol do we use for the input? X is length of the square cutout. So if the name is B and the input is X, our function is called B of X. What's the rule that will give us the area of the base? What's the rule? Length times width, and you just write what they wrote up there. It's the length times the width. Okay, now we're going to represent the area of the base when that cutout is 4.1. Go. So just when that area is, when the cutout's 4.1, don't calculate, just represent it.
Should we still use B or do we have to add?
Oh, no. You want the, well, what is the function, the name of the function f? What does it output? Does it output the area? No, f outputs volume. Here you want to represent the area of the base. So which one are you going to use, f or b? B. Now, f will give you volume, and now this new function b gives you area. What's that? Do I just do 2 and 3? Yeah, go on to number 2. Yep. After part B, go on to number 2. I mean, go on to number 3. Yeah, 3 and 4. So for 3 and 4, you're writing out meanings. You're writing out sentences. Do 3 and 4. Go on and work on 3 and 4. You're writing out, no calculations, you're writing out what these mean. Let me clarify number 3. So number 3 is saying you're going to plug 1.2 into F, and then you're going to subtract what you get when you plug 0.5 into F. That's going to give you a number, right? When you do all that work, you'll get a number. This question is asking you, tell me what that number is. What does that number represent? What is the meaning of that number? So you're writing out a sentence. This is the area of the base when it's 3 o'clock and I'm standing on my head. Okay? That's the type of thing you're writing.
Number 4.
Number 4. Number 3. No, number 3. 3A and B. You're not writing out any numbers. You're writing out this expression would find the number that means this. How many jelly beans my brother eats when it's 10 a.m.? Okay? How much rain we got in Tempe last week? Does it make sense? That's the kind of answer you're doing. Okay? So when you do that, you're going to get a number. What does that number mean? What is that? Okay, did you get it? So 3A, really key. This goes back to what we did earlier in class. F of 1.2 minus F of 5. When you do all that work, what will that number represent? change in volume. Which change in volume? When you start with the cutout length at? No, you start at the lower value. You're going to start at 0.5. You're going to increase the cutout length to 0.2, and this number will be change in volume when you do that. I'm going to post Wednesday's homework. I'll post that this afternoon.